topic we are going to discuss today is also about the last stage of an amplifier. So, all are last. Now, today's topic is on power amplifiers, and as we all know, power amplifiers always would be the final stage in an amplifier. Now, if you take the example of the public address system which we have been talking about, starting from the microphone all the way to the loudspeaker, you would see that power amplifiers come just before the loudspeaker. It is the power amplifiers which actually drive the signal through the loudspeaker, which makes us to hear the audio well. Now, power amplifiers are very different from all that we discussed so far. We talked about common emitter amplifiers, we talked about common base amplifiers, we talked about common collector amplifiers. In those amplifiers, our consideration was mostly gain, input resistance, output resistance, and so on. And when we talked about feedback amplifiers, we saw how we could improve these parameters, especially input impedance and output impedance, depending on the type of the amplifier. We saw how we could get almost, let us say, close to ideal conditions by applying negative feedback. So, our consideration in the case of feedback amplifiers was to how to make our amplifier, an ordinary amplifier, how to make it, say, close to ideal. When we talked about multi-stage amplifiers, we said multi-stage is the way you go about when you actually implement an application such as a public address system, or even in an op-amp. We saw that you have at least 2 to 3 stages, and the final stage is the output stage or the power amplifier stage. So, here the considerations which we are going to talk today are very different from all that we talked about so far. Now, let us get into the topic. I would quickly go through the kind of topics I plan to cover depending on the time. Now, when we talk about power amplifiers, they are conventionally classified into what are called class A, class B, class AB, and class C. What we will do is, we would see the classification initially, and then we will talk about class A power amplifiers. We would see their transfer characteristics. We will also observe their signal waveforms. We will also see about their power dissipation and power conversion efficiency, we will see. Then we will talk about class B power amplifiers. Once again, we will see the transfer characteristics, the power conversion efficiency, and we will also talk about power dissipation. Now, once we talk about class B amplifiers, we need to talk about what is called the crossover distortion, and we also need to wonder, or rather worry, about how to reduce the distortion, and therefore we have this intermediary between class A and class B called the class AB power amplifiers. We will see how it operates, and we will talk about a simple biasing scheme for a class AB circuit, and finally we will just quickly talk about power BJTs and some of their basic characteristics. Now, one very important thing to remember in this particular topic is the transistors which we use here are very different from the ones which we were considering so far, hence the word power BJTs. Now, so far the BJTs we were using, they were what are called small signal, they are even sometimes called small signal amplifiers, such as BC147 or 547 or BC109 and so on. Whereas when we talk about power BJTs, the consideration is very different. They are primarily meant for high power application. Therefore, in terms of their size also, they will be very different. So, we will see quickly, we will talk about power BJTs. Now let us get some idea about this topic of power amplifiers or the output stage in an amplifier. Now the power amplifier or the output stage, as I said right in the beginning of my lecture, is the final stage of any practical amplifier. Why is it so? Because it is in the final stage you have to connect the output of the amplifier to the load. So power amplifier, its main function is to drive the load. Now again, another very major difference from all that we talked so far and this particular amplifier is, so far we were talking about large signal levels. We did not concern ourselves with small signal. Now in this particular amplifier we are actually concerned about not the small signal but large signals. Why is it so? Because after 2 stages of amplification or 3 stages of amplification, let us say in a power, let us say a publicator system, the signal levels we are talking about are very large. Take the example of a publicator system. The signal levels you are talking about could be of the order of say 20 or 30 volt peak to peak, could be quite high as compared to small signal. When we talk about the BJT amplifier, when you did in the laboratory, the levels you are talking about are say typically at the most, let us say peak to peak 1 volt. So here we are talking about large signals and that makes a very, very big departure from all that we are talking about. So therefore whatever models we use so far, which were the small signal models, we cannot use them anymore. So this is something which we need to keep in mind very much. So therefore we will not use any small signal model. And if you remember from the example we took in the, when we talked about multi-stage amplifiers, I took a numerical example to illustrate a multi-stage amplifier, and there I said that the multi-stage amplifier, the final stage of the multi-stage amplifier in that particular example had a unity gain. So almost always power amplifiers are designed for unity power gain, unity voltage gain, and they have large current gain, therefore they have large power gain. So even though they have unity voltage gain, because of the large current gain they have large power gain, and we know that power gain is nothing but voltage gain times current gain. Now because we are talking about large signal currents at the output side, power amplifiers must have very low output resistance. So this is definitely easy to understand. Whenever we have to drive a lot of current, we need to ensure that the source resistance is very small. So here we have a controlled voltage source, so we need to make sure that the resistance are small. When we say small here, we would be talking about most of the time resistances say less than an ohm, much less than an ohm. Again, higher the power application, much lower the output resistance. Now when we talked about small signal amplifiers so far, we took something for granted. Why did we talk about small signals? We talked about small signals because we said that if you could keep your input signals in a common emitter or a common base or a common collector amplifiers to be say about 10 millivolt or so, we said then we could assume that the distortion, the nonlinear distortion is almost not there. So therefore we could assume the amplifier to be linear, and in almost all the cases we would find that the small signal approximation is fairly accurate. Now here unfortunately, since our signal levels are much higher than 10 millivolt and they could be of the order of tens of volts or at least a few volts, generally it would be tens of volts. We talk about a kind of a power application. Now here therefore you will have nonlinearity. So one very important parameter in the design of a output stage or a power amplifier is the amount of total harmonic distortion, or what is called the THD. So power amplifiers will always have some amount of THD as compared to normal small signal amplifiers. So we need to kind of specify this. So when you buy, if you buy say a public address system, they would mention that the total harmonic distortion is so many dBs and so on. Now the THD, or the total harmonic distortion, is the RMS value of the harmonic components of the output signal excluding the fundamental. Now again, another extremely important parameter when we talk about an output stage is the efficiency. Now this is something which we did not worry at all so far. We did not even use this word efficiency so far, because when we talk about a small signal amplifier, the signal levels we are talking about are very, very small, say millivolts, and the typical power we are talking about again would be at the most, let us say 10 to 20 milliwatts, very, very, very small. Therefore even though our amplifiers were highly inefficient, that did not bother us, because even if you are talking about, let us say, a 10% efficiency in an amplifier which is delivering, let us say, 10 milliwatt of power, you are talking about at the most 100 milliwatt of power, which we don't even bother about. 100 milliwatt is such a small number. But unfortunately, when you talk about a power amplifier, since the power levels we are talking about are large. By the way, when we talk about power amplifiers, we generally talk about applications which deliver power of say more than a watt, let us say typically 10 watt or above. You would say 10, let us say 5 watt or so. So we are talking about powers order of say 10 watt or more. Therefore efficiency is an extremely important parameter for a power amplifier, because now it is not just the amount of power we are wasting, but in some applications that may be an important consideration, but in most of the applications it is the amount of power you need to dissipate that will be the main concern. So therefore if I have an efficiency of only 10%, and if I talk about, let us say, 10 watt, then I need to somehow dissipate 90 watts of power. Now that is definitely not an option. Therefore we have to really be concerned about efficiency. Now low efficiency would automatically mean much larger power dissipation, and the reason why power dissipation is a problem for us is the following. Two reasons. One is it is very difficult to dissipate the power and to keep the temperature, and I am sure all of us are familiar with let us say if you visit a small let us say a mobile transmitting station or any electronic application where you have large amount of power, you will always see a huge amount of cooling being done through fans and so on. Sometimes even they would use coolants to do that. Now so that is one concern, to dissipate the power. Now another very major concern is we are talking about semiconductor devices. Now so far we never ever worried about how much our device would get heated up or so, because the powers we are talking about were a few milliwatts. But now we are talking about high powers. Therefore we need to be concerned whether our device would get heated up. Now if our BJT gets, let us say, heated up beyond say 150 degrees, it will get damaged immediately. It is completely useless. In fact it may not be a bad idea to maybe just touch the body of one of these power transistors which you would find on the bottom of, or just the rear side of a public address system, or sometimes even in power supplies. It is a good idea to just touch it. You will always see it will be warm, and we are talking about 150 degrees, which is very, very high. So we need to ensure that the temperature of the BJT junction temperature does not increase, and it is kept within as close as possible to the ambient temperature. Now we are talking about say an application where you are using battery, like especially a portable kind of application, then the power efficiency is the concern there is the amount of reducing the drain in the power supply. Now, as we said, the transistors used here are very special transistors, and typical power dissipation capabilities of these transistors would be a few watts and sometimes maybe hundreds of watts. For example, a very popular NPN transistor which you may be familiar is 2N3055, which has a dissipation power of 125 watts. So we are talking about large power dissipation values. Now we could design an output stage using both discrete and integrated circuits. Both are there in use. Now these days you would find a lot of power amplifier ICs available, and which has much better features than the discrete ones. But what we are discussing here are basically concepts. So it does not matter we are talking about discrete or integrated. Now, as I said right at the beginning, when we talk about power amplifiers, we classify them into class A, class B, class C and so on. Now this is done on the basis of the shape of the collector waveform in response to the input signal. Now we would assume the input signal to be sinusoidal. Now what we have here is a sketch of the typical collector current waveforms in 4 of these categories. Now let us look at the first one. Now the class A amplifier, what we see here is that we have the signal here, sinusoidal signal here, and this is the collector current. Now what you would see here is that even when the signal is negative, even at the extreme negative excursion of the signal, you see that there is still current, which means that this particular current IC, which is the quiescent current or the operating current, is greater than the peak value of the signal. So this is a very important feature of a class A amplifier. So in a class A amplifier, you would ensure that even for the largest swing of the signal, the amplifier will always have current. This current, the negative peak, the current does not go below 0. We would ensure that. Now that is class A. When you come to class B, what we see is that in a class B amplifier, we would actually use 2 devices, one device for one half cycle and the other device for the other half cycle. So what we see here is the typical class B classification, where the current would be, in the previous case it was flowing throughout. So if you talk about a conduction angle, here it was 360. In this case the conduction angle is 180 degree. So that's the classification of a class B. And as I said, because you are only taking care of one half cycle, you need to have 2 devices working in tandem or in a complementary fashion. So one device would take care of the positive half cycle, the other device will take care of the negative half cycle. So that's how a class B amplifier works. So the conduction angle here is 180 degrees. Let's now talk about class C amplifiers. Now class C amplifiers are amplifiers where the conduction angle is less than 180 degrees. Now class C amplifiers are very special cases and we will not worry much about them. Now class C amplifiers are used in very high power applications. So generally these are very special kind of applications. We will not worry much about them. What is important for us are class A, class B and class AB. Now class AB is something which is in between class A and class B. We said class B, the conduction angle is 180 degrees, and in a class A it is essentially 360 degrees. Now class AB is a case where the conduction angle is greater than 180 degrees, but less than 360 degrees. So it is slightly more than 180 degrees, and we will see why. So let us look at these in some detail. So what we saw in the signal which we just now saw was, in a class A amplifier, the amplifier is biased in such a way that the DC operating current without the signal, that was greater than the peak of the signal current IP. We saw that. Now that is why we said in the case of a class A amplifier, the amplifier or the device in that amplifier conducts for the entire 360 degrees. Now what are examples of class A amplifiers? Now the amplifiers which we studied so far, common emitter, common base and common collector, these amplifiers belong to the class A category. So these are amplifiers where the device conducts for the entire 360 degrees, the conduction angle is 360 degrees, the entire period. There is no interval during the signal the device is not conducting. Now, so that is, so our common emitter, common base and common collector belong to the class A category. Now what are class B? As we saw from the waveform there, the collector waveform of class B amplifiers, what we saw that these amplifiers were kind of biased at 0 DC current. So therefore they conducted only when the signal came, and we said you would have two devices. So normally there is no conduction, and as soon as the signal comes, one device conducts for the one half cycle. So one device would take care of the positive half cycle, the other device would take care of the negative half cycle. Therefore since they conduct only for half period of the sine wave, the conduction angle is 180 degrees. Now as I said, because they conduct only for 180 degrees, you need two such stages, or let us say two such devices. Now what is actually done is you would combine the currents from these two stages, so that when it flows into the load, you have a kind of continuous conduction. Now class A B amplifiers, as we saw in that the waveform there, these are biased at not 0. In class B we would bias it at 0, which means if there is no signal, the amplifiers are, the BJTs are off. But in this case, we would bias the transistor at a very slight value of DC current, but this will be much smaller than the peak current of the sine wave. Now if you compare this with class A, a class A amplifier, we biased making sure that the biasing current is much greater than the peak of the sine wave. But here we would bias it at a extremely small DC current. We will see why and how much. So therefore the class AB category, the transistor conducts for a period greater than 180 degrees, but much smaller than 360 degrees. Now class AB also requires two class AB stages. Now again, just like the class B, you would kind of combine the currents from these two transistors, and they are combined so that they would flow in a combined fashion into the load. Now when we talk about class C amplifiers, now this was the waveform we saw in the last one, where we saw that the transistor conducts only for an interval which is less than half period. So the conduction angle was less than 180 degree. Now the output current waveform is actually a kind of a periodically pulsating waveform, and so these kind of amplifiers are used for very high power application, such as a, let us say, a transmitting station, where the kind of powers we are talking about are in the orders of kilowatts or hundreds of watts. In those kind of situations, you would use a class C amplifiers, and then what is done is the currents are passed through a parallel LC circuit tuned to the frequency of the input sine wave, and we will not, this is a very special class, and we will not study this, because this is generally you would never ever come across a class C amplifier. Now let us look at class A amplifiers in detail, and then let us see why class A amplifiers are not preferred, even though they conduct for the entire 360 degrees, which is the ideal situation. We will see why they are not. So we need to see in detail their operation. Now you can think of a class A power amplifier as an emitter follower. In fact, that is the most popular choice, because we know that emitter follower has low output resistance, and we saw right in the beginning that one of the most important requirement of a power amplifier is that it should have low output resistance. Therefore, the obvious choice from the point of view of what we studied so far is to choose an emitter follower. Now let's look at a typical class A amplifier using emitter follower, and then let's see how it works. So what we have here is basically a two transistor kind of combination. Now what is done here is this stage here, which we see in the bottom, that is Q2, and this diode here and a resistor. Now these are the Q2 is biased through this particular diode in such a way that there is a current I flowing all the time, a DC current I flowing all the time. Now what we will do is, when we apply a signal here, we want to see how exactly the output looks like. Now as we said, in this particular case, since we are talking about a power amplifier, we are actually interested not in the small signal operation but in the large signal operation. So let us see how this particular circuit operates. So to have a recap, what we have here is a Q1, which is the one which gets the signal, and it is biased through this two transistor combination, and we have a emitter current flowing, which is IE1, and then what happens is a current IE1 will be equal to I plus IL, and IL is the current flowing through the load, and we have the output voltage taken across the load. Now what we need to see is, for seeing the large signal operation, we need to find out the transfer function, rather the transfer characteristics of this particular stage. Now what we saw that it was biased with a constant current I supplied by that second transistor, and we saw that the current flowing through the first device IE1 is equal to I plus IL, where IL was the current through the load. Now we need to ensure that when we choose I, we need to ensure that the bias current I must be greater than the negative peak of IL, in order to ensure that Q1 is always in the active mode. So this we saw when we saw the signal waveforms. So when we design such a stage, we need to ensure that the particular current is chosen such a way that it exceeds the negative peak, so that even when we have the negative peak, still you have a certain value of DC current. Now we can write a very simple equation for the transfer characteristics, which, as we saw, the signal was applied to the base of that transistor, and we have a VB drop there. So output was, this was an emitter follower, so output is taken from the emitter. Therefore the output voltage is nothing but input voltage minus VB1, and this is an NPN transistor. So this is the equation. Now the important thing to remember here is this value of VB1 depends on IE1, and it definitely also therefore has a bearing on the value of IL. Now if we can neglect the small variation in VB1 due to IE1 variations, and we know that the being an exponential characteristics, for a very small change in VB1 you would get large current variations. So if you assume that these variations in VB1 are small, then from this equation we see that the V out versus V in characteristic is linear. Now if you sketch it, this is how you would get. Now from that particular equation we wrote, V out is equal to Vi minus VB1. So we see that, we see this particular characteristics. Now what is important to notice here is we assumed this to be linear, which is not a bad assumption. Now we need to be concerned about the upper limit and the lower limit, and on the x axis we have Vi, and the y axis we have V out or V naught. Now the upper transistor being in a common collector kind of a stage, we are taking output from the emitter, therefore the maximum value, the emitter voltage, the maximum value of the emitter voltage is nothing but the VCC, the positive VCC minus VC sat, that is the maximum voltage you can have. So till that point you can operate. Now coming to the absolute, you can, when you talk about the negative half, you can think about two limits. Now in case one, the absolute limit is the limit when that particular transistor would go into saturation. So the bottom transistor, let us see the circuit again. Now so this is the first transistor Q1 here. Now Q1, the output voltage here can rise as high as VCC minus VC sat. So that is the upper limit here. Now coming to the lower limit, the extreme is minus VCC plus VC sat. So that is the extreme limit. But again, depending on the current which you have chosen here, you can have another limit. So in case you are constrained by the current you have chosen there, then the negative limit will be minus of IRL. We must remember that we have chosen I such a way that the peak of it is greater than the negative peak. So if that is the constraint, so the lowest value would be minus of IRL, but the absolute limit would be minus VCC plus VC sat. Now so we have these equations here which we talked about. Well, let's have a look at the output signal waveforms of this particular transistor stage we saw now. Now what we can say is that if you can choose the bias current I properly, then the output voltage VO can swing from approximately minus VCC to plus VCC, and the quiescent value would be V out is equal to 0. Now we can kind of sketch say 2-3 waveforms. One waveform would be, we would like to see the kind of the VC1 waveform. When you apply a signal, we want to see how the VC1 signal varies. So we know that since the VC1, since we are talking about a common collector stage and the output is at the emitter, so therefore VC1 is nothing but VCC minus V out, because V out is same as VE, and VC is nothing but VCC. So VC1 is nothing but VCC minus V out. Now we can also kind of sketch another waveform which would tell us the value of I. Now we can also kind of sketch the instantaneous power dissipation, which is defined as VC1 times IC1. So, if we look at these waveforms, what we see here, the first one is the V out waveform, and we said that we would assume that it goes from the two extremes. So, this is the kind of maximum possibility. On the positive side, approximately it can go to plus VCC. On the negative side, it can say approximately go to minus VCC. So, that is the V out signal. Now, corresponding to that, if you look at the VC1, we wrote the equation there as VC1 is equal to VCC minus V out. So, if you do that, we see that this is if you substitute our V out there, and we see that as far as VC1 is concerned, it can go from all the way from, if you go to the extremes, we would see that it can go from 0 all the way to 2 VCC with a kind of a quiescent value being VCC. So, when V out is 0, we have VCC, but with signal the VC1 changes all the way, it can vary from 0 all the way to twice VCC. So, that is as far as the VC1 waveform is concerned. Now, if you look at the IC1, the current flowing through the top transistor, if you think about that IC1 current there, now the quiescent value is I. So, when there is no signal, it is I. Now, with signal, it can go up on the positive side all the way to twice I. On the negative side, it can go all the way to 0. So, that is the excursion of the collector current, and we are just at the border of class A. Now, what we have here in the last waveform is the power dissipation, the instantaneous power dissipation, which is PD1, which we see is have a very interesting waveform. Now, the quiescent value of current was I, and the quiescent value of VC1 was VCC. So, when there is no signal, the power dissipation is VCC times I, but with signal we see that the power dissipation varies. So, what we see here is something very interesting, which is very different, and this is one of the reasons why we do not like to have a class A amplifier. So, from this particular waveform, we see that this is a very important a sketch. So, this particular one, what is telling this is about the power dissipation of that transistor, which is Q1. Now, what it says is that you have the maximum dissipation when there is no signal. So, if you have no signal, then you are going to have the maximum dissipation. So, that is something very strange. When we are not using it, the VJT is getting heated up the maximum. With signal, the power dissipation changes. So, this tells us, gives us a clue about its efficiency. Now, let us work out some numbers, write some expressions for the power conversion efficiency of a class A amplifier. Now, by definition, power conversion efficiency is defined as the load power PL, the power delivered to the load, divided by the power supplied. Now, in our example, we had two power supplies. So, that power let us call as the total power supplied by the power supplies as PS. So, PL by PS is what we would define as efficiency, because this would directly tell us about the power conversion efficiency. Now, with a sinusoidal output voltage with a peak, let us say VO max, VOM, the average load power PL would be PL is equal to VOM by root 2. So, this would give us the RMS value. So, VOM divided by root 2 the whole square divided by RL, which is nothing but half of VOM square by RL. So, this tells us the power supplied to the load. Now, the power drawn from the power supply is, we can find out from the PD1, which we said is VC1 IC1. Now, we know that the and that particular, so the power conversion efficiency we can see as, by substituting, we would see that this would be 1/4 of VOM square divided by I RL VCC. Now, we know that the the maximum which we can allow, the output cannot rise more than VCC, or it cannot, it has to be within IRL. Therefore, the maximum efficiency we can get here is for the condition when the VO maximum is equal to VCC is equal to IRL, and for that condition the maximum efficiency possible is 25%. So, this gives us an extremely important result as far as class A amplifier is concerned. So, for a class A amplifier, the maximum theoretically possible efficiency is 25%, and we know that even this we said is an approximation. The signal, input signal cannot approach VCC, we assumed it to be VCC. So, therefore, we said it is 25%. So, most of the time when you talk about a class A output stage, you cannot operate at that kind of input level. So, typically the kind of efficiency you are actually get in a normal operation is somewhere between say 10 to 20%, because most of the time your output swing would be definitely the peak of the output swing would be less than VCC. So, we see something which is extremely important to remember, that is class A amplifier, even though it gives us the least distortion because it conducts throughout, is the least efficient. And we said an extremely important consideration, it was not a consideration when we talked about small signal amplifiers, because the powers where we are talking about there were in a few milliwatts, and the device getting heated up was not an issue at all, because the collector currents typically we talked about were a few milliamps at the most, and we never ever had a problem of power dissipation. But here we are talking about several watts, several tens of watts, or in some cases let us say hundreds of watts. If you are talking about a public address system, you are talking about at least 100 watts, or if you are talking about a major public address system, you are talking about thousands of watts. So, efficiency is one of the most important considerations. So, therefore, we can conclude that for an output stage we should never ever use a class A amplifier, unless otherwise our power requirement is extremely small. If our power requirement let us say is less than a watt, then class A is the best choice. But if our power requirement is more than a watt, or if we are let us say several watts, then definitely we should not go for a class A stage. Now, let us look at the next class of circuit, which is actually a class B amplifier. Now, in a class B amplifier, we, as we discussed right in the beginning, since it conducts only for 180 degrees, we have to use two stages. Now, what we have here is basically a complementary pair of transistors, an NPN and a PNP. So, the top transistor we have an NPN transistor, and the bottom transistor we have a PNP. So, it is used in a complementary fashion. Now, we can see from the signal here that when your input is positive, the upper device, the QN, the PNP, the NPN transistor will conduct. When the input is negative, the PNP transistor will conduct. So, the way it is connected, we know that both of them cannot conduct at the same time simultaneously, they cannot conduct. So, when you talk about a class B, this is what we talk about. Ideally, what we expect is that the top transistor would take care of the positive half cycle, and the bottom transistor will take care of the negative half cycle. Now, let us look at the circuit operation in detail. Now, when the input is 0, so let us have a look at it. Now, when the input the voltage is 0, what we can say is that both of them are off. Now, as you keep increasing Vi on the positive side, we know that this particular Vb, you need at least 0.5 volts. So, till Vi equals 0.5, Qn cannot conduct. Once Vi exceeds say about 0.5, this particular voltage may not be exactly 0.5, but somewhere around that, we know that once it exceeds that say about 0.5 volts, the Qn would start conducting, and the current now would start flowing into the load. Now, during the entire positive half cycle, the QP device, the bottom PNP device would be off. Now coming into the negative half cycle, when Vi, again when Vi is equal to 0, we know that both of them are off because there is not enough forward bias. When Vi goes negative and the VEB or the VBE, when it is less than minus 0.5, when VBE is less than minus 0.5, the PNP transistor would conduct. Till then it cannot conduct, and beyond that point the PNP would conduct, and you would have a current flowing into the load. Now, so this is what we discussed. When Vi is equal to 0, both are off. When Vi is positive and it crosses about 0.5 volt, Qn conducts. So beyond 0.5 volt, we can say the transistor, the upper transistor, the NPN transistor works like a emitter follower, and we can say that V out is equal to Vi minus VBN. This N stands for that NPN, VB value of the NPN transistor. And during this period, the QP, the PNP transistor will be off as long as Vi is greater than 0. When Vi is less than 0 and when it goes below minus 0.5, QP turns on, and this now acts as a emitter follower. The output voltage V out in this case we can write as Vi plus VBP. Mind you, in a PNP transistor the emitter would be more positive, so whereas in an NPN transistor the emitter would be less positive compared to the base. So hence this changes. Now Qn will be off for the entire duration when the input voltage is less than 0. Now let us sketch what we talked about. Let us sketch it into a transfer characteristics. Now this characteristic is extremely important. This particular graph has a lot of significance in the design of a power amplifier. Now what we have here is what we just said in words. So on the positive, what we have is Vi on the x axis, V out, the output of the amplifier, on the y axis, and we said that when it is 0, both are off, no current flows. Now till about 0.5 volts the output is 0. Once the input goes above plus 0.5, the current starts flowing, the NPN transistor conducts and the current starts flowing, and then you have an emitter follower, and you have a slope of unity slope. And then at the upper end we know that it cannot go beyond VCC minus VC sat because it will go into saturation. So that is the upper limit. Coming to the negative side, we see that once the PNP transistor can conduct only when the input goes below minus 0.5, and once the input is below minus 0.5, you have an emitter follower again in action, and the slope will be unity, and again you have a negative limit there, would be minus VCC plus VC P sat. This P stands for the PNP, saturation voltage of the PNP transistor. Now having seen this, so we might wonder why, if this, and it is obvious seeing from the transfer characteristic that we are definitely going to get a distorted output, but then why are we interested in class B? That will be very clear once we see the power conversion efficiency calculations of a class B amplifier. Now a class B power amplifier, once again we can write the same equations which we did for class A. The average power we wrote there of the output sinusoid with a peak amplitude VOM is PL equals half VOM square by RL. Now the current drawn from the power supplies will be half sinusoids, because we know that each of those transistors conduct only for half cycle, and when the NPN transistor conducts, the power is drawn from the positive supply. When the PNP transistor conducts, the power is drawn from the negative power supply. So we have current drawn about half sinusoids drawn from the power supplies, and the peak amplitude there will be VOM, which is the maximum value, by RL, that is the peak current drawn. Now the average power drawn from the power supplies we can write as PS plus, which stands for the positive power supply, equals PS minus, which is the power drawn from the negative power supply, and that will be 1 by pi VOM by RL into VCC. Now, so the total power supplied, we could, that will be double of that. So the total power supplied will be twice VOM VCC divided by pi RL. So now we can write an expression for the power conversion efficiency. So if you do the substitution, we would get this expression. We will see eta, the power conversion efficiency, as PL by PS as half VOM square by RL, which is the power delivered to the load, divided by the power supplied, which is 2 by pi times VOM into VCC by RL. Now this we would get it to be pi by 4 into VOM by VCC. Now eta max happens when we have VOM equal to VCC. Now that gives us 78.5. This is an extremely large number. Compare this with the class A amplifier. With the class A power amplifier, we said the maximum possible was 25%. Now there is a lot of difference between 25% and 78.5%, extremely large difference. So now we are very, very clear why we are interested in class B amplifier. We see that the interest in class B amplifier is primarily from the point of view of the efficiency. Now what we have here is a plot of that equation which we just now wrote there, with VOM, rather V maximum on the x axis and the power dissipation on the y axis. Now mind you, the power dissipation would be the power supplied minus power delivered. So whatever power you supply and the whatever, if you subtract the power delivered to the load, now the remaining power is dissipated in the device. So we would see that in a class B amplifier, the power dissipation would keep increasing as you keep increasing the input voltage. Now it reaches a peak, and the peak power dissipation is actually twice VCC square by pi square RL there, and at that particular point the efficiency is only 50%, but even that is very high compared to a class A output stage. Now this happens when the input signal is twice VCC by pi. So that gives us the the value of the input signal at which we get maximum power dissipation. Now the point at which we get maximum efficiency is at we saw that is the point at which where our maximum, the V maximum is same as the VCC. At that particular point we have an efficiency of 78.5%. Now this gives us a very, very good reason why we should go for class B. So class B power amplifiers or the output stages are very good from the point of view of power conversion efficiency, and 78% is not at all bad, it is extremely good. Now unfortunately there is a problem. This we saw from the transfer characteristics. We saw that in the transfer characteristics we had a dead zone. Dead zone meaning we had a region, that region was plus minus 5 when the Vi is within plus minus 0.5 volts. We saw that during that period we had the dead zone, meaning we have no output. So because of this we would have what is called crossover distortion. Now crossover distortion is extremely disturbing. It's a very, I would suggest it's a very, very good idea to design a very simple emitter follower like the one which we have done. Maybe some little biasing changes can be there, and you would see that if you apply a signal, you could then apply, you could just maybe speak into one such class B amplifiers, and you can listen to the sound from a loudspeaker, and then you will understand what you mean by crossover distortion. Now the crossover distortion would be extremely disturbing. This is because of the reason that our ear is extremely sensitive. It can pick up even the smallest distortion, and again that is people dependent. Some people are much more sensitive than others, but crossover distortion is easily distinguishable. So if you give a signal, especially a voice signal, maybe a music signal, you put it through a class B amplifier and then you put it to a speaker, it will be very evident what is crossover distortion. The sound would be very displeasing. So we need to find, so class B is very good from the point of view of efficiency, but it is very bad from the point of view of crossover distortion. So we need to find a middle path. We need to find a way of reducing the crossover distortion without sacrificing much on the efficiency. Now this is where the next class of amplifier comes into picture, and class AB amplifier is the amplifier which is actually used in practice. So as we discussed so far, class A amplifier, we also discussed class B amplifiers. Both these amplifiers are actually done only for the sake of theoretical analysis, and we, from our discussion so far, we saw that both of them are bad from the point of view of an actual application. And the problem with a class A amplifier was the class A amplifier was very good from the point of view of distortion. It had no distortion because it conducted for throughout the period, but we saw that a class A amplifier unfortunately has only 25% efficiency, while a class B amplifier we saw that was very efficient. We could get a maximum efficiency of 78.5%, but unfortunately because of the dead zone which we have in the transfer characteristic, we have a what is called a crossover distortion, which is displacing and which we cannot have. Now in a class AB amplifier, as the name itself suggests, is kind of a, let us say, a mix of both class A and class B. In a class A, we have the conduction throughout the period of the sine wave. In a class B, you had a conduction only half cycle. So in a class AB, you would have a conduction which is greater than 180 degrees, but that is less than 360 degrees. Now let us have a kind of a look at say a kind of a conceptual diagram where we have what we have done is, so you could see the signal being applied to the base here. Now the difference between this particular circuit and the circuit of the class B amplifier was, in the case of a class B amplifier, we did not have this small biasing here. Here we have introduced a small battery called VBB by 2, and we here also. So both the transistors we had introduced a small battery here. Now the purpose of this particular battery is to ensure that when there is no signal, when VA is equal to 0, we would like the NPN transistor to be just at the threshold of conduction, because if we adjust that voltage on the higher side, then the transistor would conduct, then we will get into class A situation throughout. If you make it too small, then what will happen is it will have distortion. So this particular voltage need to be very, very carefully chosen. So let us tentatively take this value of this voltage to be 0.5 volts, but this is a voltage which we need to choose very carefully. Now again, it is not a bad idea if you have one of those old transistor radios with you, a portable transistor radio. Most of these radio sets would have an adjustment for this crossover distortion. If you look at any kind of a portable application like a tape recorder or a radio, all of them would use a class AB, and what is done is, in kind of cheap portable applications, this voltage adjustment of this voltage is very difficult. So what is actually done is, you would actually apply a signal, you would listen because this is a, you have a loudspeaker there. So you would listen to the sound, and then you would have a kind of a potentiometer arrangement which would give you some voltage. So what is done is, you would slowly adjust the voltage in such a way that, and what is generally done, a symmetrical kind of arrangement is done, so that the kind of a positive of that gets applied, negative of that applies here, or you can even think of two separate pots. So what is done is, you would apply voltage in such a way that you are just at the threshold, that the distortion just disappears. Now in fact, occasionally what people do to do this is to connect an ammeter in the VCC path. Now if it is class B, no current will be drawn from VCC when you apply no signal here. Now as you keep changing this VBB voltage here, if as you go from say slightly conducting to more conduction, a huge amount of current will flow here. So that's how this current, this particular biasing is done, but we will not worry about it. So let's assume that we know this particular value and we have applied that particular voltage here. So what now happens is, when you apply a signal here, the output now is going to be Vi plus, we would have this particular bias kind of adjusted here. So what we would get is the output would, then we would get rid of this particular distortion there, so the dead zone would disappear. In this particular case of the PNP transistor, we have the base being brought negative. So we could see from here that through, since the emitters of both the transistors are connected together, we need to ensure that this potential is less by VBB by 2. So this is how we would implement a class AB amplifier. Now once we do this, we can see that we get a linear characteristics ideally, and as I said rightly, you need to choose this particular voltage very, very carefully, and that's when we actually design a class AB amplifier, you would see that this is one of the most challenging jobs, or one of the most difficult part of, because if you go from say no conduction to conduction, you need to ensure that you don't drain the supply too much, because if you have too much current flowing, you are playing with the efficiency, and the efficiency will drastically come down. Now what we have here is a kind of a typical biasing of class AB amplifier, which is typically used for kind of an IC kind of an application. This is the way you would bias, and you could also do this with kind of diodes. These days you would get, in fact what we get occasionally, you would get some of these matched diodes or transistors in kind of arrays, which could be used for this purpose, but this kind of biasing is easily done in an IC. So what is done here is, you would first decide what is the voltage you need here to ensure that it is just at the threshold, and accordingly you would choose a current, bias current. Now we know that VB voltage is related to the current, bias current, by the equation Vt ln I by Is. So by adjusting this value of I bias to the desired value, we could get whatever is the desired value of VB here. So essentially what we are doing here now here is, we are ensuring that this particular one is you have 2 VBB, 2 VBE between these two bases. So that would ensure that if it is properly biased, we can ensure that if we are just at the threshold of conduction, and that would ensure that we have fairly large efficiency, but not as large as 78%, but at the same time not as small as 25%. So depending on the biasing here, we would be able to get different kind of efficiency. So far we studied, as of now we discussed class A amplifier, we also talked about class B amplifiers, we also talked about class AB, and we saw why class AB amplifier was required here.